welcome to chapter 1 called payable. We have a lot to read here, so I will just go through them fast and give brief explanation of what each paragraph is saying. All right, so up until now we've covered quite a few function modifiers. It can be difficult to try to remember everything, so let's run through a quick review. So I wouldn't read all this they are saying here, but I will just give a brief explanation. So we have 4 different types of function modifiers. We have private, internal, external, and public. Now, what are the differences? Now, a private function is only accessible or is only callable from functions inside a contract. And now you know what a contract is. A contract is this block of code that you've declared right here. Okay, so that's what a contract is. Right, so it's only accessible and callable within the contract it's declared, right? Whereas internal, right, is much like private, but the only difference is that internal can be accessible or is accessible to other contracts that inherit it, like this. Remember how we do inheritance by using the is keyword. Okay, so and public, or let me say external. Let's start with external. External is only accessible. That's external functions are only accessible outside the contract, which means the outside world, right? Okay. Next, public functions are accessible both externally, that's the outside world, and internally, that's within your code base, right? Within your code base, which means including contracts that inherit from that contract. Okay, so that's it. And then we also learned about pure and view modifiers. View functions, we said, are functions that only read data from the blockchain, but they do not modify or change any value, and they do not store any value to the blockchain. Whereas pure functions are functions that will read value off the blockchain. Pure functions are functions that neither read value or store value to the blockchain. They neither read, store, or even change values on the blockchain. All right, and both of these functions do not cause gas, but they only cause gas when it's called internally by another function within your code base, right? Now we also had custom modifiers, and we looked at 2 in our last lesson. That's only owner and above level, right? And for this type of modifiers, we create them, right? And we declare and we write our logic that we want these modifiers to do for us, right? So that is that. And another thing is that we can stack modifiers on a function, right? For example, if you look at this function right here, this function uses 2 modifiers, only owner and another modifier, right? So you can actually stack modifiers on a function, right? And those modifiers will run before the function is executed. All right, so the payable modifier is a new modifier we want to be looking into in this chapter. Now payable functions are what are the number one thing, the major thing that makes Solidity and Ethereum very special, because it gives our functions the ability to accept Ether, that's receive Ether, and Ether is the currency that is being spent on the Ethereum blockchain. Now, when you call an API function on a normal web server, if you've worked with the regular Web 2 programming as web development, now when you do that, you cannot send money, right? You cannot send money or cryptocurrency with your function call, right? You cannot. But in Ethereum and with Solidity, it's very possible to send money, to send Ether with your function call. So that's what makes Solidity very different from other languages. All right, so and this is the essence of blockchain, right? So with this, we can be able to pay a certain amount of money to a contract, right, before it executes a particular function. Probably you want to buy an NFT on the blockchain, right? Or you want to buy an asset on the blockchain. This is what enables you to pay money on the blockchain, and then what the function is called, right? If you've ever tried. So let's look at an example. Here is an example. We have the contract called online store, and then you have a function here, buy something function, and you can see it's marked as payable, and it's an external function. That means it can be called by people in the outside world, right? So you can see that here we are requiring that a value of 0.001 ether is sent at the call of this function, right? Message.value is what indicates the money being sent, right? Message.sender is the person calling the function, while message.value is the amount of ether sent at the call of this function, right? So every function that is marked payable must have a message.value. All right. So, and if this passes to true, that's if the caller of this function is sending this amount of ether, then it will what? If so, some logic to transfer the digital item to the caller of the function will be executed. So, right, and the logic is down here. You can see transfer something logic, right? And then who do you want to send it to? To the caller of the function, which is the message the sender, right? So that's simply how it works. Yeah. So message.value is just a way of seeing how much ether or Ethereum was sent to the contract at call, right? And what you're seeing right here is how someone would call the function on the front end, right? So here you see, all right, so let's say this on an online store, right? And then on the online store, a buyer calls the buy something function, and then you can see a particular account is associated with that call, and then the value of which is the amount of ether this account is sending, right? So that's how it's going to be implemented on the front end. So it says you can think of transaction as an envelope, and the parameters you pass into the function are like the contents of the letter, right? And then adding a value, which is, in this case, the money, the Ethereum being sent, it's like what? Putting cash inside the envelope. So that's how you should basically think of a transaction on the blockchain. If a function is not marked payable, and you try to send ether to it as above, the function will reject your transaction. All right. So take note of that. So let's put this to test. Let's create a payable function in our zombie game. Let's say our game has a feature where users can pay ETH to level up their zombies. The ETH will be stored in the contract which you own. This is a simple example of how you could make money on your games. All right, so we'll define a uint called level up fee. All right, and set it equal to 0.001 ether. So we just come here and say uint called level up fee, and set it equal to what? 0.1 ether, like so. All right, so number 2, create a function named level up. Right, it will take one parameter, which is a zombie ID, and it's going to be a uint. It should be external and payable. Right, so I'll just say function called level up, taking one parameter called zombie ID. Right, remember to put the type uint. Okay, so it should be external and payable. Remember, sorry, external and not payable, which means this function can receive money. Right, the function should first require the message that value is equal to what? Level up fee. All right, so here we just want to require that message dot value is equal, right, to what? Level up. Sorry, level up. Oh, I'm just gonna copy this. All right. So that, okay, the M here, sorry. Okay. And then it should then increment this zombies level. So on the next line, let's just copy this, right, and paste this right here. So the zombie level will be incremented. So let's check and see if we're correct. Okay. All right. So to the next chapter. Okay. So welcome to chapter 3 called Zombie Battles. Now that we have learned about payable functions and contract balances, it's time to add functionality to functionality for zombie battles. Alright, following the format from previous chapters, we'll organize our code by creating a new contract for the attack functionality that imports from the previous contract. Alright, so we want to start by implementing zombie battles for our application, right? So let's put this to test. Here it says, let's review creating a new contract. Repetition leads to mastery. If we can't remember the syntax for doing these, check zombiehelper.so for the syntax, but try to do it without picking first to test your knowledge, right? So we should be able to do this, right, without looking at this file. So the first thing we're asked to do is to declare at the top of the file the Solidity version. So I'm gonna just copy this, right? So how do we declare the Solidity version? By using the pragma keyword, and then followed by Solidity, then the Solidity version, right? So number 2 says import from zombiehelper.so. Okay, zombiehelper.so, zombiehelper.so. Okay, so we're importing the zombiehelper file, and then next declare a new contract called attack zombie attack that inherits from what? Zombiehelper. Leave the contract body empty for now. So I'll just say contract here, then what? Zombie attack inherits what? Zombiehelper. Okay, so then followed by curly brackets. Alright, so I think we're done with this. So let's just check answer to see if we're correct. Okay, we have a little problem on this line, and okay, I think, yeah, we're supposed to add a dot and slash at the beginning to indicate file directory. Okay, to say, all right, this file is on the same directory with this file, with this the file we're currently on, right? So that's how it works. So try again. All right, so I'll see you in the next chapter. All right, so welcome to chapter 4 called random numbers. Great. Now let's figure out the battle logic. All good games require some level of randomness. So how do we generate random numbers in Solidity? The real question here is you can't. The real answer here is you can't, right? Well, at least you can do it. You can't do it safely. Let's look at why. Right, random number generation via KShark 256 So the best source of randomness we have in Solidity is the K-SHA-256 hash function. We could do something like the following to generate a random number. Alright, so this is an example of the K-SHA-256 at work, right? So you can see here we have the K-SHA-256 function and then the encoded packed function. Remember that before passing anything into the K-SHA-256 function, you have to pack it first, right? To convert it to a type that it is compatible with, right? So you can see we are passing in a bunch of values here: the round nouns, message to sender, and noun, right? The round nouns has been declared above here as 0, while the message to sender is the person calling this function, the address of the person calling this function, and then noun is the timestamp. That's the timestamp of that current moment, right? So that's how it works. So on this line we are increasing the value of what round nouns. So basically the value that is going to be generated, the hash that is going to be generated from calling this function, is going to be completely random, because each time the value of noun changes, and also each time we're incrementing the value of round nouns, right? So we are assured of a very random hash variable, hash value that is going to be returned, right? So basically after it is returned, we are converting it into a unit here, right, and storing it into a variable. All right, so yeah, one more thing to note here. You can see here we have a modulus 100, the value that is going to be returned after converting it into an integer. We're going to find a modulus 100 of it, right? So this is basically going to return the last 2 digits of that value, right? So if we have, let's say, it's going to return 4 and 3. All right, so if you use your calculator to find the modulus 100 of a number, you will see that it returns the last 2 digits, right? So I'm not going to read through this paragraph because I've already explained what this code does, right? So here we have something. It says the method is vulnerable to attack by a dishonest node, right? Okay, so it says here that this method of generating a hash, right, it's not 100% safe, right? It can be vulnerable to attack, and it can be vulnerable to attack because because of how the Ethereum blockchain works, and the way it works can be exploited. I don't want to read through this paragraph, but you can basically just read through this paragraph to see how vulnerable or how the Ethereum blockchain can be exploited if this method is used. But just keep in mind that it's not safe, it's not 100% safe, secured. So then the question is, how can we generate random numbers safely in Ethereum, right? So please take your time and read through this paragraph to understand how the this method is not safe and how it can be exploited, right? So how can we generate a random number safely in Ethereum? All right, so because the entire contents of the blockchain are visible to all participants, this is a hard problem, and its solution is beyond the scope of this tutorial. You can read this Stack Overflow thread to find out, more about how random numbers can be generated safely in Ethereum, because right now it's beyond the scope of this tutorial. But one common way that is used to generate random numbers in Ethereum is through something called an oracle, right? So we have third-party oracles like Chainlink Oracle, right? So that's one oracle that can be used to generate random numbers in Ethereum. Okay, so I would show you the oracle. So let's just put this test. All right. So it says let's implement a random function we can use to determine the outcome of our battles, even if it isn't totally secure from attack. All right. So give our contract a uint called what? Rundowns, and set it equal to 0. So let's just define a uint here called what? Rundowns, and set it equal to 0. And number 2 says create a function called rand mod, rand modulus. It will be an internal function that takes a uint called named modulus and returns a uint. So I'm gonna just create a function here and name it what? Rand mod. Okay, so I'm going to take in one parameter called what? Modulus. All right, so and I'm gonna return it returns the uint, right? So we're just gonna put return uints there. So number 3 says the function should increment round nouns using the syntax this. Alright, so I'll just copy this. I'll copy this and paste it. Alright, so just add my plus plus at the end. And then lastly it says finally it should in one line of code calculate the uint typecast of this hash of this, passing this in, and return the value modulus, right? So you say, wow, this is a bit mouthful. If you didn't follow that, just take a look at the example before we generated a random number above, right? So this example, that's what they're referring to. So I'm gonna just copy this and change out the values to fit our work. So here we're just going to return it directly. We're not going to store it in any variable. So I'll just say return, right? And then I think the same things we are passing in here is the same thing we are passing in here also in our code, right? So all right, let's click check answer. Okay, no, so I will change this to modulus here. We should be modulus, not hard coded as 100, right? So remove this. All right, so check answer. So something is wrong. Okay, I forgot to put the internal keyword. It says the function should be internal. So let's try again. So something is wrong. What is wrong? What's wrong? Okay, I have a 0 at the end here, which is not supposed to be there. So I'll just delete this and then try it again. And voila. All right, so see you in the next tutorial. Chapter 5, zombie fighting. Now that we have a source of some randomness in our contract, we can use it in our zombie battles to calculate the outcome. Our zombie battles will work as follows. You can choose one of your zombies and choose an opponent's zombie to attack. If you are the attacking zombie, you will have 70% chance of winning. The defending zombie will have what 30% chance of winning. All zombies attacking and defending will have a win count and a loss count that will increment depending on the outcome of the battle. If the attacking zombie wins, it levels up and spawns a new zombie. If it loses, nothing happens except its loss count incrementing. Whether it wins or loses, the attacking zombie's cooldown time will be triggered. This is a lot of logic to implement, so we'll do it in pieces over the coming chapters. Alright, so we'll be implementing all these features and in this application. So we'll start in this chapter to create the function and And then as we move along in this lesson, would so as we move along in this chapter, we would in this lesson, sorry, we would implement every one of all these features, right? So let's put this to test. Give our contract a uint variable called this. All right, so I'll just copy this and set it equal to 70. Okay, so I'll just say uint set what 70. All right, so create a function called attack. It will take two parameters, zombie id, a uint, and target id, also a uint. It should be an external function. All right, so I will just say a function called what attack, and then a uint called what zombie id, and then a uint called target id. Okay, all right, and it's also going to be an external function, right? So it says that we should leave the function body empty for now, so we would implement it in later chapters, right? So let's click the check answer button to see if we're correct. All right, so I'll see you in the next chapter. Hi, welcome to chapter 6, refactoring common logic. Whoever calls our attack function, we want to make sure the user actually owns the zombie they're attacking with. It would be a major concern, security concern, if you could attack with someone else's zombie. So can you think of how we would add a check to see if the person calling the zombie is the owner of the zombie ID they're attacking with, right? So we want to add a check, right, to see if the person calling the attack function is attacking with his own zombie, right? So give this some thoughts and see if you can come up with the answer on your own, right? So pause this video, give it some thoughts. How do you think we can add this check, right, to check if the person calling this function, that's the attack function, owns the zombie they want to attack with, right? So now if the require statement came to your mind, then you are very correct. Congratulations, right? So this is just how we're going to be doing the check, right? So we have used this same line of code in other places like change name function, change DNA function, and feed and multiply function. Okay, here we have the feed and multiply function. Do you see how we are performing a check here? We're checking to see if the person calling this function owns the zombie, right? So, and also in I think also in change name function, see, we're using the check here also, and we're using the check here also, right? So here, sorry, so it's the same thing we're going to be doing here. The same logic we'll need for the attack function. Since we're using the same logic multiple times, let's move this into its own modifier to clean up our code and add and avoid repeating ourselves. Okay, so because we are using this logic, across board in multiple functions, it's best, or it's much more idealistic, or is best, and it's much more cleaner and much more organized to extract this logic and put it in a modifier, and then use the modifier across board wherever we need it, right? So let's put this to test. We are back to zombie feeding. So since this is the first place we use that logic, let's refactor it into its own modifier. So number one says create a modifier called owner of, to take one argument called zombie ID. All right, so it said we should create a modifier here. So I will just go here and create a modifier called what, owner of. All right, so it's going to take an argument called what, Alright, so the body should require that message.sender is equal to. Alright, so basically this same thing would need here, right? That's what it's saying there. Right. So then if you can refer to zombie helper.so if you don't remember the syntax for the modifier. Alright, so then remember that in every modifier we need to add a second line that tells the compiler to continue with the function execution, right? So this line just says, all right, if this passes to true, then continue with the execution of the function, right? So that's that. Change the function definition of feed and multiply such that it uses the modifier owner of, right? So where is feed and multiply function? All right, so I'm just going to say owner of. Then remember that this modifier takes in a parameter, right? And that parameter is zombie id, and we already have zombie id here, so we're just going to pass it in right here also. Yeah, okay. And by doing this, we don't need this check here again, so we're just going to remove this line. All right. Yeah, number 3 says now we are using a modifier, you can remove this line. All right, we've already done that, so yeah. So I'll click the all right, so see you in the next chapter, right? Great. All right, so welcome to chapter 7 called more refactoring. We have a couple more places in zombie helper.so where we need to implement our new modifier owner of, right? So yep, so we want to change out, you know, those functions where we use that require statement, right? We want to change it out and use this owner of modifier. So number 1 says update change name. All right, so we want to update this change name. So what we're just going to do is remove this and then use the modifier here, owner of. Remember, we need to pass in the id, the zombie id. All right, so also we do the same with the change DNA function. So let me just copy this and then paste right here. All right, so yeah, I think we're done with this pretty fast, right? Very pretty fast. So let's see. All right, so congratulations. See you in chapter 8. Okay, so welcome to chapter 8, back to attack. Enough refactoring, back to zombie attack.so. We are going to continue defining our attack function now that we have the owner of modifier to use, right? Okay, so let's put it to test. We want to continue, you know, creating the attack function. All right, so put it to test, add the owner of modifier to attack to make sure the owner owns zombie id. All right, so number 1, we need to add the owner of modifier here, right? And then remember to pass in the zombie id. All right, so that's 1. Number 2 says the first thing our function should do is get a storage pointer to both zombies so we can more easily interact with them. So the both zombies in this case, I think the both zombies here is referring to the zombie that is attacking and the zombie that is being attacked on, right? So how do we get a storage pointer to them? So it says declare a zombie storage named my zombie and set it equal to this, right? So let's declare a zombie storage. I think it's right here inside the function zombie, right? Storage named what? My zombie and set it equal to what? This. Okay, so I'm gonna just copy this and then paste it right here with my semicolon. And then number 2 says declare a zombie storage named what? This. So just copy this and set it equal to the same thing down here. I remove this named here, right? Of course. And I'll set it equal to, you know, this with the target ID in the brackets, right? So I'm too lazy to type. I don't. All right. So then number 3 says we are going to use a random number between 0 and 99 to determine the outcome of our battle. So declare a unit called named rand and set it equal to the result of randmond. All right, of the randmond function with 100 as an argument, right? So we want to get a random number from 0 to 99, and this is what we'll be using to determine our outcome after the zombie has attacked on another zombie, right? So we already have a function that generates a random number, right? The randmond function here. So we'll just create a variable, a uint called rand, and set it equal to the call of this function. So a random number will be returned at the call of this function and to be stored here, right? So we'll use that number to generate the outcome of the attack. So remember, we need 100 here as the argument. 100. Okay. All right. So let me quickly explain what's going on here. So this first line, right, is retrieving or is getting the zombie that wants to do the attack. That's the zombie of the owner who wants to perform an attack, while this other line is getting the zombie that the owner wants to attack. That's the zombie that wants to be attacked on, the target zombie, right? So we call it the enemy zombie, right? So then this line is just getting us a random number. All right, so let's check and see if we're correct. All right, so I'll see you in the next chapter. Okay, so welcome to chapter 9 called zombie wins and losses. For our zombie game, we're going to want to keep track of how many battles our zombie have won and lost. The way we can maintain a zombie leaderboard, that way we can maintain a zombie leaderboard in our game state. We could store this data in a number of ways in our DApp, as individual mappings, as leaderboard struct, or in the zombie struct itself. Each has its own benefits and trade-offs depending on how we intend to interact with the data. In this tutorial, we are going to store the stats in our zombie struct for simplicity. Yes, and call them win count and loss count, right? So we want to keep track of the wins and losses of each zombie. So we're just going to be adding that as a property in our zombie struct, right? So let's put this to test. Say modify our zombie struct to have 2 more properties: the win count and the loss count, both of which are of uint 16, right? So uint 16 win count, then uint 16 loss count, right? All right, so now remember, by doing this we are saving memory, we are saving space, right? Because the compiler does a packing when you put properties of the same type side by side like this. So the compiler does a packing, a packing that saves space. All right, so when writing properties in a struct like this, you do not want to take a property that is of same type, and bring these over here, right? This will occupy more space, so you want to put properties that are of the same type side by side, right? So that's just it. All right, so number two, right, they said note, remember, since we can pick units inside struct, we want to use the smallest unit we can get away with. A unit 8 is too small since 2 raised to power 8 is what, 256. If our zombies attack 1 per day, we could overflow these within a year, but 2 raised to power 16 is this. So unless a user wins or loses every day for 179 years straight, we should be safe. And so they're just simply trying to explain why the unit 16 we chose here is the best option, because if we had chosen a unit 8, for instance, a simple 2 raised to power 8 is already equal to 256, right? So which means in less than a year we're going to we're going to exceed this number. Our property is going to overflow this number, because as if our zombies attack once per day, right, we'll definitely exceed this number, because we have 365 days in a year, and this is way much lesser than that, right? So this is a much more safer choice to choose, because 2 raised to power 16 is this, right? And this, we cannot finish it in 179 years straight. So now that we have new properties in our zombie struct, we need to change our function definition in what create zombie. Change the zombie creation definition so it creates each new zombie with 0 wins and 0 losses. Alright, so these are create zombie function. Alright, so these are zombie create function, and at this point here where we create the zombie, we want to account for these new parameters that we just added, right? So we're going to be creating the zombie with 0 wins and 0 losses. Okay, so right here where we passed in the parameters of the struct, we're just going to add 2 more parameters for the win count, right? So the win count is going to be 0 and 0, so just like this, right? So 0 representing win count and the next 0 representing loss count. I mean, at the creation of a zombie, you want to make the zombie win count and loss count to be 0, because it hasn't attacked anything yet, right? So that's that. All right, so check answer and see. All right, so I'll see you in the next chapter. Okay, chapter 10, zombie victory. Now that we have a win count and loss count, we can update them depending on which zombie wins the fight, right? In chapter 6, we calculated a random number from 0 to 100. Now let's use that number to determine who wins the fight and update our stats accordingly, right? So each time a zombie attacks, right, either whether it loses or wins, we need to update the win count and the loss count property, right? So then how are we going to determine if a zombie wins or loses? We're going to use that random number we generated, which is this, right? So let's put this to test. Number 1, create an if statement that checks if rand, that's this, is less than or equal to the attack victory probability. That's this that we've created before, right? So let's create an if statement, right, that checks if rand is less than or equal to the attack victory probability, right? So if this passes to true, we're going to execute some function, we're going to execute the body, right? So it says if this condition is true, our zombie wins. So increment zombies win count. All right. So how do we increment my zombies win count? So we just say my zombie will call, right? Remember that my zombie is representing the zombie that the owner is using to attack, right? So my zombie dot what dot win count plus plus, right? So we're incrementing it by 1, which means, hey, this zombie has gotten 1 win, right? So increment my zombie's level, right? Because it has leveled up. Each time a zombie attacks and win, it levels up. So we just say, hey, dot level plus plus, then increment my enemy zombies loss count, right? So we're going to increment the enemy zombies loss count. So just copy this and then increment its loss count plus plus. So this zombie has lost one more time, so we have to increase the number, right? So number D says run the feed and multiply function. Check zombie feeding.so to see the syntax for calling it. For the third argument, species, pass the string zombie. It doesn't actually do anything at the moment, but later we'll add some extra functionality for spawning zombie-based zombies if wanted to, right? So this species here is determining how would I explain it now? Or you will understand more about this species as we move on, all right? So but for now, just pass in zombie as the parameter, as the argument there, right? So we'll call the feed and multiply function here. Multiply. I will just copy this. All right. So we're going to pass in the parameters of the feed and multiply function. All right. Let's see what the parameters it takes. Where are we? All right. So it takes a zombie ID, target DNA, and the species, right? So pass in what? The zombie. Sorry, an underscore zombie ID. Then the target DNA. That's the enemy zombie, right? The enemy zombie is the target. Enemy zombie, then the ID. So we have to do something like dot DNA. Sorry, not the ID, the DNA. So dot DNA, right? And then the species zombie, right? So we're just calling the feed and multiply function here and passing in what the zombie ID. That's the zombie ID of the zombie we are attacking with. Now we're also giving it what the target zombie DNA. Say, hey, this is the DNA of the zombie we want to attack. That's the target, and then the species is zombie in this case. You understand what species means later on, okay? So let's check and see. All right, so there is a little problem here. Okay, I think the problem is the semicolon, right? So let's try again. All right, so see you in the next chapter. So welcome to chapter 11, zombie loss. Now that we have coded what happens when the zombie wins, let's figure out what happens when it loses. In our game, when the zombie lose, they don't level down. They simply add a loss to their loss count, and their cooldown is triggered, so they have to wait a day before attacking again. To implement this logic, we will need to add an else statement. Else statements are written just like in JavaScript and many other languages. So this is an if else statement here. So the difference is just that there is an else here and then a block of code that we execute if this doesn't pass, right? So we're going to add an else statement to this our if function that will handle the case of when our zombie loses, right? Because this block of code is already handling the case of when the zombie wins, right? So we'll just simply add an else statement here that will handle the case if, in this case, if this doesn't pass, then it means the zombie lost, right? So let's add an else statement that said if our zombie loses, increment my zombie loss count, right? So we just add an else statement here, else with the then increment my zombie dot what loss counts, right? We want to increase the loss count on the loss property on the zombie, right? So we just say plus plus. So we're just saying, so this simply just means, hey, this zombie has lost one more time, right? So number 2 says increment enemy zombie win count, right? So definitely if the zombie lost, it means his enemy won over him, right? So we need to increase the win count of that zombie that won, right? So win count, right? So that's that. And then lastly, it says run the trigger count cooldown function on my zombie. This way the zombie can only attack once per day. Remember, trigger cooldown is already run inside feed multiply. So the zombie's cooldown will be triggered whether he wins or not, whether he wins or loses. So what this is simply saying is that in this case of when the zombie wins, the trigger cooldown function is already being executed when we call this function right here, because this function has already been called inside this function. If you check the feed and multiply function here, you would see that we are calling it right after at the end here, right? So we've already handled the cooldown for this part of the code, so we need to handle it here also, right? So we just call the trigger cooldown function here directly, right? Because whether the zombie loses or not, whether the zombie loses or wins, you need to call the cooldown, because you don't want a zombie feeding more than once per day, right? So that is that. And I think does it accept any parameter? It accepts a zombie, right? So we're just going to pass in my zombie right there. All right, so that's that. Let's see if we're correct. Okay, there's a little problem. Oh, I forgot to put my semicolon. All right, so great. Something is the problem again. What's the problem? Oh, I think we got the spelling of this wrongly. All right, so we put a capital D here instead of a small d. So that's why I like copying and pasting sometimes. So I just do this, and then I think we're good to go. Oh shit! What the hell is wrong with this? Okay, I think it's because we are losing a third bracket at the end here, right? So we're losing a third bracket. So all right, see you in the next chapter. Welcome to chapter 12. Wrapping it up, right? Congratulations. That concludes lesson 4. Go ahead and test out your battle function to the right. Claim your reward. After winning the battle, your zombie will level up. Your zombie will increase its win count. You will spawn a new zombie to add to your army. Go ahead and try the battle, then proceed to the next chapter to complete the lesson. Alright, so let's perform an attack, right? We've built out the attack functionality, so let's see how it works out, right? So this is it here at work. So assuming this is our zombie, so I'm just going to click on this and see what happens. So you can see that the zombie attacked and then a new zombie is generated, right? Says Iota has been slain in battle, which means the zombie that was attacked was called Iota, right? Your zombie win count is 1. Your Iota's loss count is, so this particular zombie has lost many times, right? So this is the new zombie that was created. This is the DNA of the new zombie. All right, so try another combination. So let's try again and see what it gives us this time around. So I'm gonna attack one more time, and then voila. Is this the same zombie? I don't know if it's the same zombie. Okay, let's check and see if it gives us the same zombie again. Oh, it keeps giving us the same zombie, right? I thought it's supposed to be random or something. Well, anyway, that's just to show you how it works. But in real sense, I think it's gonna be random. Okay, so try. So next, right? Next. So great. So this is the end of chapter lesson 4. Sorry. So congratulations if you have gotten this far. All right. So I'll see you in chapter 5.